First of all, of course, I would like to thank Benjamin, Olivier, and the other Olivier, who is not here, for the kind invitation. And then I would like also to apologize. I won't talk about spin mechanics. I won't talk about imaging. I will only talk about how we can detect one single electronic spin that yield to the only one single nuclear spin, and how we can manipulate it also, one single nuclear spin, and how we can perform quantum gates and even a quantum algorithm, which is the Grover sorry, algorithm. So this work was performed in Grenoble, and Wolfgang also took a big part of this work, even if he's in the KIT, he's still somehow in Grenoble. And mainly I will talk about 3 PhD today, and the last one, Clément, and the previous one, Stéphane, and another one, Romain. And of course, I'm going to talk about molecular magnets, and those molecular magnets, this one, which is a special one for us, TBPC2, was synthesized in Karlsruhe by Svetlana and Mario Ruben. So what we have done during the last years or decades had one purpose, and the purpose was to go to the nuclear spin detection. And the detection is only by electrical means. So we developed different kind of detectors. One is a microsquid, and with this kind of superconducting device, you can measure an assembly of a molecular system. And the first idea to measure only one single spin carried by a molecular magnet was in fact to increase the coupling in between the molecular magnet and the superconducting loop. And then, to increase this coupling, the idea was to decrease the nanobridge which is here. And then there was this detector, the nanosquid, but it took time to develop it, and physics in this kind of system was so interesting that we never deposited a molecular system on it. Actually one with holmium, to be honest. But at the same time we developed a different kind of detector with graphene nanotubes, which lies on the surface, suspended nanotubes, and you heard about this on Monday. Wolfgang talked about this. And today I'm going to talk only about this scheme where the molecular magnet is trapped in between two electrodes. And then we'll measure the current through the molecular system and try to measure the nuclear spin states. So first, why do we use molecular magnets? Because they are fantastic objects, and they carry a magnetic moment, and there is a strong anisotropy, and the magnetic moment, if we talk about the spin, there is a various type of spin that we can play with, going from 0, not really interesting, to even 40. And of course, they exhibit quantum properties, like the tunneling effect, for example. And this tunneling effect was measured a long time ago. And for example, if you take an assembly, so a crystal of iron 8, and you measure the magnetization as a function of the external magnetic field in the double well configuration, first you saturate all the spin in up configuration, and then when you sweep the magnetic field, at one moment you can have a resonance in between the plus 10 and the minus 10. I have the Fabio's problem. And then you can reverse the spin. And then it's why when you measure the magnetization, you see a step here that does depend, of course, on the sweeping rate of the magnetic field. And then you can still increase the magnetic field, and then you have another resonance, and then you have a relaxation, meaning that, yeah, you have another step. But this is for an assembly of molecular systems, so an assembly of spin, and the idea is really to measure in our system one single spin. Of course, you can do some other things with molecular magnets, like studying the interference phenomena, like Berry's phase. When you reverse the electronic spin, it can be constructive or destructive. And of course, in the past, there was some really nice measurement, in this case on iron 4, showing that you can manipulate coherently the spin of this system. But if you look at here the time, the coherence time is really low. And this is due to the fact that this is a crystal. And in fact, there is dipolar interaction, and those dipolar interaction will introduce some decoherence in the system. Okay, and last but not least, sorry, there is almost an infinite number of molecular magnets we can play with, which can be dangerous because when you start to study one, it can take years, so you have to choose wisely the system you want to investigate. And then what do we want to do? So two things. First, there was this proposal almost 20 years ago by Leuenberger and Loss to use a manganese 12, and the different states that you can have in the manganese 12 with a spin 10 in order to perform, to implement the Grover algorithm. But then you have to be able to go from a 10 to 6, so it's a multi-photon process. It's almost impossible to perform, at least at this moment and at low temperature. But the idea was really to use molecular magnet for quantum computing, or at least to be able to perform some coherent manipulation. And the other idea for what I'm going to present you comes from Kin, and it deals with silicon and impurities that you have in silicon, and the use of the DC-Stark effect in order to tune the resonance of the nuclear spin qubit that you have in the system. So basically, I'm going to talk about how we can manipulate the spin in a molecular magnet, and how we can manipulate it is using not the DC-Stark effect, but only the AC-Stark effect, meaning that we can modify the wave function of the electronic spin, and due to the fine interaction with the nuclear spin, we will tune the resonance of the qubit. So my outline is like this. I will present again the TBPT2 single molecular magnet. You heard about it on Monday, but I will go quickly on this one. And then I will present you how we can electrically read out the electronic spin that yields to the nuclear spin states, then how we can manipulate the nuclear spins, and then how we can play and manipulate everything at the same time and perform Hadamard gate and the Grover algorithm. So first of all, I said that there is almost an infinite number of molecular magnets. It comes from crazy chemists that can synthesize whatever they want, and sometimes they synthesize whatever we want, physicists. And this molecular magnet is has been synthesized a long time ago, and in fact, our choice was mainly due to this different reason. The first thing is that the magnetic properties are mainly carried by this ion here, which is a Tb3 plus ion, and the two ligands that are here will protect basically the magnetic properties of this ion. Another thing is I will show you how we can trap one single molecule, and locally it hits quite a lot the system. So this molecular magnet can undergo some high increase of temperature. It was deposited at different kind of temperature, and here is a signature of the TBPC2, so it still survives to this kind of high temperature. As we're going to make transport measurement, it was also important that, that the electrons are going to flow to the molecular magnet won't go directly to the Tb3 plus ion. Otherwise, you modified drastically the magnetic properties, which is not the point. And of course, as Wolfgang said on Monday, that we can add some special ligands, for example, in order to graft on some defects of the nanotube or on some other materials. And then it's also because if you have this TBPC2, you can add a layer, and then you have two magnetic centers. And so this already exists. And you can even dream of more, and actually this molecular magnet already exists, and then you can think about a scalable, and this is absolutely a dream. Of course, you cannot manipulate each individual atoms and address them and measure them, but basically in principle it's scalable. Principle, of course. So here is a molecular magnet we investigated. A central part is a Tb3 plus ion. And then, due to a strong spin-orbit coupling, you end up with S equals 3, L equals 3, and then you have a magnetic moment J equals 6. And if you look at the Zeeman diagram, the first excited states are at high temperature. I mean, there is a big gap, 600 Kelvin. And as all the measurements we're going to perform are at really low temperature, 20 to 40 millikelvin, at the end we end up with either up or down electronic spin. But there is something else, sorry, each time. So first, not something else. I will talk about nuclear spin after. This is a squid measurement of an assembly, and what you see is that at 0 here, you have a strong increase of the magnetization. This is due to the fact that you have a QTM, and this is all the process, Landau-Zener process. And when you go across this avoided level, either you undergo reversal, and then you reverse the electronic spin, or you don't undergo reversal, but at one moment you undergo a direct transition. But today I won't talk at all about the direct transition. I will only talk about quantum tunneling of the magnetization. Okay, but then there is also nuclear spin. The nuclear spin is 3/2. Magnetic moment is really tiny, and this is not really important. What is important is the hyperfine coupling with the electronic spin. And what is also important is the quadruple term here, because at the end we end up with 4 states, and due to the quadruple term here, the level spacing are at different frequencies, 2.5, 3.1, 3.7. Okay, so again, the Zeeman diagram. So when we sweep the external magnetic field, we can undergo a quantum tunneling of the magnetization, and then if we add the nuclear spin to the sketch, instead of having only one avoided crossing, we have 4, and at this 4 position, color code is important. It means that the nuclear spin remains the same. So if at this point I can measure a reversal of the electronic spin, the nuclear spin remains the same. And there is only 4 positions. Okay, this is an experimental work. We do everything at home, going from the fabrication to the fridges, as Wolfgang said, and 3D Victor magnet, and also the electronic, except the synthesis of the molecular devices. So the idea is to have this configuration, meaning that we have a source, drain, the molecular magnet which is trapped in between, and underneath we have a gate, and then we only perform transport measurement at really low temperature. So first, just want to say quickly how we can trap this single molecular magnet. It's an old technique. It's called electromigration technique. So you start from a nanowire. In this case, it's a gold nanowire. And then you apply a voltage across the nanowire and measuring the conductance at the same time. First, you see a decrease, of course, of the conductance. It is a Joule effect. And then a slight increase. This is due to the rearrangement of the aggregate that you have here. And then a sudden drop. And then if you make a zoom here, what you have is some quantized steps. And the ideal picture is this. You have a chain of atoms of gold in this case. So it's how we can make a nanogap. And making a nanogap is not so hard, but trapping a molecule is harder. And it's based on a statistic, because before putting the nanowire into the fridge, what we do, we deposit the molecule at room temperature. So it's just a droplet of the solvent plus the molecule we want to investigate. So this is performed at room temperature. And then at low temperature, we perform the electromigration. And then we just hope that one single molecule will be trapped in between the source and the drain. So it's statistical. It works, of course. Some students are lucky, it works the first time, and then they measure during 2 years. And some others are less lucky, but I mean, it's 5 months maximum so far, so it means that it works. Now, but I always compare to the fabrication of the perfect device when you go to the clean room. And those devices, just a nanowire, it's 1 week to prepare those devices. And when you're talking about superconducting qubits, for example, sometimes it's 1 year of fabrication. So at the end, it's basically the same, except that we don't control so many things here. Okay, so if you're lucky enough, you have this configuration, and then you can start to perform transport measurement. And the idea is to say, when you have transport, as you need high energy to add 1 electron to the ion here, in fact, the current will flow through the ligand. So the picture is here. You have your quantum dot, which is here. I'm going to call it the readout quantum dot, under the influence of the spin dot. So electronic spin up or down. And then what we perform is only transport measurement at the first time. And this is not so nice Coulomb diamond, but as you're going to see, it's good enough. This is a charge degeneracy point, and here we have some Kondo effect, which is quite interesting to extract the exchange coupling between the spin dot and the readout dot. So now we want to reverse the electronic spin. And in fact, in this configuration here, there is an exchange coupling in between the quantum dot, the ligand, and the spin dot, the electronic spin that you have here. And due to this exchange coupling, depending on the orientation of the electronic spin, the chemical potential in the quantum dot is different, meaning that the transport through the quantum dot will be different. So if we sweep the external magnetic field, and if you undergo a reversal, chemical potential of the quantum dot will be different, then differential conductance will be different. So that's the electrical detection of the orientation of one single electronic spin.
The reason I'm asking is that chemical potential has a symmetry different than
because the coupling, the exchange coupling in between the electronic spin and the spin which is in the quantum dot is slightly anisotropic. And this is only due to that. Otherwise, I fully agree. If everything is fully symmetric, no change in the chemical potential. Okay, so this is one jump, but then we have more. And of course, it's only one single molecular magnet, so we have to perform statistics. So one measurement, one jump, another measurement, and so on and so on. And in this measurement, it was 75,000 sweeps. And big drawback is when we sweep the magnetic field, we sweep in 1 second. So the readout is one electronic spin in 1 second. But that yields, you see clearly that there is only 4 positions where we have jumps. And when we make the statistic, you have nice histograms that yield to the nuclear spin states. So in 1 second, we can detect the nuclear spin state. Okay, so this is old already, 2012. And then the molecular system is quite robust, as Wolfgang showed, because it can be deposited on a nanotube, or you can have another kind of detection. We're using the vibrational mode on the nanotubes. But the signature, I mean the really perfect signature to say, okay, this is really the molecular magnet under investigation, or those 4 peaks that are the signature of the 4 nuclear spin states in the molecular system. Okay, now I want to talk about the lifetime of our nuclear spins. So what we do, we sweep back and forth the magnetic field, and each time we have a jump, we made the derivatives, then it's only a point, I mean it's a peak, we take the maximum, and then we can make what is called the nuclear spin trajectory. And this helps to extract the lifetime of the nuclear spin. So this is the nuclear spin trajectory, and then we focus on this one, and we make the statistic over a few hours, and then we yield to the number, the population as a function of time, and we stay, for example, in this 3/2 for a long time, which is approximately 25 seconds. For the lower, also approximately the same time, and here approximately twice less, I mean divided by 2, only because when you are here you can excite or you can relax to the other state. And this is for one sample, this is for another sample, and just meaning that the lifetime is quite long. But it's not so long, in fact, to be honest, because you have to compare this to how fast we measure. And the lifetime is long, but we measure in 1 second. So long enough for what I want to show you, but not so long for what we want to do in the future. Okay, now, so the detection of one single nuclear spin is quite easy. It's only electrical. And then we want to manipulate it. So to manipulate it, as I told you, we want to use electrical field only. In fact, we need some magnetic field in order to manipulate the nuclear spin, which is a magnetic moment. So there was this idea coming from, I mean, not this idea, it's an old idea, but they perform some nice manipulation of some electronic spin. But for us, it's not enough. There is too much Joule heating, and yeah, maximum field that you can reach is in between 3 and 10 millitesla, and 10 millitesla if you work a lot already at a millikelvin temperature. So the idea was to use only electrical field, no Joule heating first. And we can even, as you're going to see, go to much higher effective magnetic field. And so we have to modify some electrical field and use a system in order to change the electrical field into some magnetic field in order to manipulate the nuclear spin. And this is really the idea from Keane, saying that, okay, we can use a Stark effect, but instead of applying only a DC gate, we are going to apply a AC electrical field, and then we can manipulate our system. So we really play with the wave function of the electronic spin, and then we play with a hyperfine coupling in between, and this ends up with some effective magnetic field. And you don't need so much electrical field. I mean, 1 millivolt per nanometer, which is huge, in fact. But remember that our nanogap is only 1 nanometer because we want to connect a 1 nanometer molecular system. So we have a 1 nanometer nanogap. So we just have to create some fluctuation in between the source and the drain of about 1 millivolt to create this 1 millivolt per nanometer. And then we end up with 0.1% of fluctuation of the hyperfine coupling. And this is approximately 100 millitesla. So that's the idea. And so first we tried this idea on the 2 lowest states at approximately 2.45 gigahertz. And the sequence is, okay, first we have to initialize, and it's not like NV center. This is unfair. It's so easy to initialize the system. For us, it's more complicated. And then to initialize, we measure the system. So we sweep the external magnetic field. We have a jump, and when we have a jump, we know in which state we are, basically. If we know in which state we are, then we can apply some RF corresponding to the resonance we want to address, and then depending on the length of the RF, we end up with some superposition of states. And then we measure, meaning that we sweep back the external magnetic field. Either we are still in the same state, or we are in the other state. That's all. Okay, so if we do that, first is the Rabi oscillation, and we measure as a function of the length of the pulse, and this is already old also. We can measure some nice oscillation, and in fact, this is 0 dBm, that's the power at room temperature of the RF generator, and if we fit the frequency of the Rabi oscillation, we end up with 72 millitesla. So it's really, yeah, due to SI-Stark effect, and we can go up to even more than this, even to 300 millitesla of effective magnetic field. Okay. Of course, we can do, I mean, we have to, when we want to really check our system, to make some Ramsey experiment, and then we have a coherence time of about 64 microseconds. So with this system, yeah, we can use the SI-Stark effect to really manipulate one single nuclear spin. And this works perfectly, and we can also tune the gate. The gate, as I told you, there is a gate underneath, so for different gates here, we can tune a little bit the resonance of our qubit system. As you can see, it's fully anharmonic, so it's not a good way, in fact, to play only with a gate for our system. Okay, we have more states. So we have 4 states, so we have 3 resonances. And it took time to really address the first and to really understand everything. And then those measurements were performed 2 years after. And as you can see, visibility is much better, for example. And you can perform as a function, of course, of the power, and also as a function of the day tuning and Chevron-like experiment. Everything is going in the good way. And then we can also make the Ramsey experiment. And then, yeah, we take only some pieces of oscillation every 50 microsecond time, and then we take the envelope, and then we end up with a coherence time which is higher than before. 2 years after, it was higher, so 300 microseconds. And then we can also make some anecho experiment, and then it's just higher. I mean, we avoid some low noise components, and we can go to the third resonance. Basically, that's the same, some oscillation, coherence time is long, and anecho experiment. And there was kind of, I mean, problem. How can we have on the same sample a coherence time for this resonance and this resonance of about 300 microseconds when this one was only 64, or let's say 70 microseconds. In fact, it's because this sample is like good wine. It's due to the fact that more you wait, less instabilities you have in your gate. And the gate induces some DC-Stark effect. So as you have some noise in your gate, of course, you induce decoherence through DC-Stark effect. And as you wait 2 years, and I mean, this sample has been at low temperature for the last 5 years, so fridges are really, really good. And in fact, we increase the coherence time, not because we perform some other tricks, but only because we waited.
How is it compared to the decoherence time of the electronic spin of terbium ion?
So we try to manipulate the electronic spin of the terbium ion, but it's impossible for us. So
it decoheres faster than it will decohere also the nuclear spin.
I agree. So I guess if at one moment we could perform the ESR directly on the electronic spin, it should be higher. Okay, so that's it. And at the end, we have 4-level systems, 3 resonances. We can play with a Rabi frequency in between 0, 0.5 to 5, or even more, 8 megahertz. And now what I want to show is that we can play. I mean, when we have this kind of ideal system, we can really play at the beginning. And the first idea was to say, can we manipulate everything at the same time? So first is we can play with the first resonance, and we make a Rabi oscillation. And then the idea was, okay, if I am in this state, I want to transfer all the information on this state. So I applied just a pi pulse. So of course it works, and if you measure the population or the visibility of the different states, you have your Rabi oscillation here, but nothing in the red one because you transfer all the information in the third state. And when you cut off the pi pulse, of course, you recover what you should have normally. The Rabi oscillation is not so nice because it was a little bit detuned on this case. So now we can play with 4 states. So we can make a Rabi oscillation and then apply a pi pulse here, a pi pulse here, and then transfer the Rabi to most excited state and the lower states. And of course it works nicely also, even if it's not perfect because we still have some remaining of the oscillation here. But this in our mind was really to say, okay, we can play with the 3 resonances at the same time because it's already, we have to play with different parameters. And now the idea is really to play with all the system at the same time. So that's the last part of my talk. I have no idea how much time I have. I don't know.
5 minutes?
5. So I'm going to go fast. And so the Grover algorithm it's not a common Grover algorithm because normally when we hear about the Grover algorithm, most of the time we have a 2-level system which is entangled to another 2-level system and so on. Here we want to use not 2-level system but multi-level system. That's QDITs. And there was a proposition also by Leuenberger and Loss to use nuclear spin which is in a gallium arsenal 3/2. And so it's perfect, we have the same. And the idea is to say, okay, if you have your 4-level system, there is a quadruple term because you need to have different resonances in between the 4 different states. If you're able to coherently manipulate each state and if the Rabi frequency is approximately the same width than the resonance, then you can really perform the Grover algorithm. And it's exactly what we have. So it was a perfect system in order to test this proposal. So what is the Grover algorithm? The Grover algorithm is only to find some element in a database. So if I take a database of 4 elements, and I know the name, but I don't know the number, the phone number, classically I just have to pick, and then I pick 1, and then I pick 2, and so on, meaning that at the end, if I really want the name and the phone number which is attached, classically I need n/2, n being the number of elements that you have in your database. So the idea to use a quantum system is to say there is a possibility when you have created the database, and to create the database first you have to apply a quantum gate which is called Hadamard gate because you need all the states to have exactly the same probability of being. But then if you know the name, you can highlight the name you want, and then if you measure you will have more probability to find it. So this algorithm means at the end is square roots faster compared to the classical one. So of course if I have a 4 elements database it's totally useless, but it's just to play and to show that it is possible. So yeah, this is a movie. This is from Karlsruhe. So here's the idea. So when you have your molecular system which is trapped in between 2 electrodes, at the beginning you have no idea in which state you are, so you have to initialize, meaning that you sweep the external magnetic field, and then you know in which state you are, you project your system. And then you want to create the database, so you apply a pulse sequence that match the different resonances with different power and different frequencies in order to create a perfect superposition of the 4 states. So that's really the database. And then you want to highlight the state that you're looking for, but you know it. And then you apply a pulse sequence in order to highlight the state you want, depending on the one you want, and then you just measure. And you have more probability to find the state you wanted. So how do we do this? Not again. So that's a mess at the beginning because you can play with the frequency, you can play with the power, and also with the time length. And yeah, at the beginning we use 3 RF generator, but at the end only 1 AWG is good enough when you have the sampling rate that match what you want. And just to say that you have to play with many parameters, and first what we did was to perform the Hadamard gate, so just creating the perfect superposition in between 2, 3 or 4 states, just to create the database. So the idea is to apply a pulse sequence in order to have 0.25% of probability of being in each state. So this works for 2, of course, for 3, and for 4. And this is a function of time. Here we see that at 140 nanoseconds, we have the perfect superposition. So that's the first gate. We create the database. And then, really the Grover algorithm, if we go from beginning to the end, what we do is first we initialize our system. And I'm going to show it only for 3 states because it was already a nightmare to perform it for 3 states, and we decided not to do it for 4 states. So I'm going to talk only about 3 states. So first we initialize. Then by applying some pulse sequence, we create the perfect superposition of the 3 states. And then we apply another pulse sequence in order to highlight the states that we want. And then by measuring, we have more, of course, chance or probability to find the state that we were looking for. And this we play only with the detuning parameters that we apply on the resonance that we are looking for. So it's exactly what we can see here. So this is the results after the readout. And in this case, we were applying after the Hadamard gate a pulse sequence in order to highlight the red. And we do it as a function of time to really clearly see the oscillation, meaning that we really highlight after approximately 100 nanoseconds the state that we are looking for. And we can do the same for the red one and the black one also. Go ahead. Yeah. So you don't project it, but you increase the probability of being in this state. It's why here, yeah, it's a little bit shadowed because it's only at the end that we really project it. But yeah, we know the state that we are looking for also. Okay? Okay, so yeah, we can play with a different parameter, and this was a simulation to say, okay, we understood quite well what's happening in our system. And I'm right on time, so that I'm lucky. So I showed you that we can, yeah, detect, manipulate, and even play with a single nuclear spin. But one thing is really bad is that we measure in 1 nanosecond. Sorry, 1 second. I would love to measure in 1 nanosecond. And so we are planning, of course, different things. So this also to say that we play with graphene electrode, but we want to do also ESR measurement to directly flip the electronic spin and then measure the conductance. And this is some measurements that we have already performed on the 2 spin qubit system. And of course, as Sebastian presented this morning, we also want to apply this kind of configuration in order to measure our molecular spin and also play with different, optically, and also to play with silicon qubits to measure our molecular magnets. So at the end, I want to really work, it was a long work, so I want to work all the PhD who worked and on this system. And Eric also, who is the guy who is building the fridges in Grenoble, and also Wolfgang, Christoph, and Edgar, who are permanent at the Néel Institute, and you for your kind attention. Thank you.